Thank you for coming out on a snowy in some parts of the state and definitely fall Utah morning. It's beautiful out there, but thank you for being here with us. I'm Annette Herman-Harder. I'm responsible for advancement at Utah State University and very pleased to welcome you to yet another Sunrise session. This is something that we do to showcase the research and the research mission of Utah State, and hopefully it's a chance for those of us within the community to learn a little bit about what goes on behind the scenes at a great research institution such as Utah State. So hopefully you will find today enlightening. I'm sure you will. I'd like to start by talking about something that's been a big accomplishment for Utah State University very recently. You may have seen some news or gotten some correspondence about the end and the completion of Utah State University's first comprehensive campaign. That's a very big deal for USU. As the phrase indicates, it is the first time that we have accomplished a comprehensive, which means covering all aspects and all facets of the university, fundraising campaign, and it was immensely successful. Unfortunately, President Albrecht is not here, but he led the team that drove it to completion, and our goal was $400 million. And in fact, what we achieved was over half a billion dollars, wrapping up at about $512 million. So big deal for USU. Not only is the number impressive, but also is what was put into place, mostly into perpetuity for USU. There were 4 named colleges that were accomplished during the campaign, over 240 scholarship endowments, which will provide funding for students to assist them with their tuition into perpetuity. There were professorships, endowed chairs, new buildings, many, many things. And perhaps most importantly, the infrastructure was laid within the leadership of USU and the faculty of USU to establish a culture of philanthropy and the many, many donors with whom the relationships were built, which numbered over 53,000 people that gave to the campaign. And I know many, many of you are among that count of 53,000. If I said 53 million, I meant 53,000. 53,000 people did support us. I'd like to acknowledge a number of folks that are here that serve on our foundation board for Utah State University. This is the board that did help guide the whole process, and we're very proud to have them help serve as part of USU's team. Scott Ulbrich is in the back, foundation board member. Richard Anderson, thank you, Richard, for coming. And David Moore is also a member of our foundation board. Another person that's a part of our foundation board, as well as our board of trustees, is Suzanne Pierce-Moore. Suzanne, thank you for coming. I'd also like to acknowledge one of my associates, Dean Scott Hinton, who's the Dean of the College of Engineering. Thank you, Scott, for being here. So this is the time when we showcase research, as I said, and this would not be possible without the very generous support of Regents Blue Cross Blue Shield. They've supported the Sunrise Sessions since its inception, and it's because of Regents that we have this lovely venue as well as the breakfast this morning, so thank you to Regents. I don't believe we have a Regents representative. We do have Regents representatives here. Thank you so much. Not only does Regents help us with this event every quarter, but they also have been the provider of our Utah State University health program for decades, and they do a fabulous job for the residents of Utah in their coverage and have for many, many years. I'd like now to introduce the Vice President of Research and the Dean of the Graduate School, Mark McClellan, and Mark will introduce our speaker today.
Good morning, everyone. Not only was it a spectacular year for development, but it was also a spectacular year for our faculty. as they hit, again, another year over $200 million in new awards coming into the research program. And it's an extraordinary statement of their hard work and effectiveness as a research entity. You would have to be deaf, dumb, and blind if you're not aware of the term STEM. The urgency by which most of the citizens of the United States are anxiously looking at our next generation and asking the question, are they prepared? Better yet, are we prepared as a nation to be competitive, to have a workforce that is second to none, is worrisome. And it's worrisome because we have questions. And it's thanks to the hard work of speakers like the one we'll be showcasing today that we're starting to see that turn around and really start to see a commitment to science, technology, engineering, and mathematics in all of what we do in terms of our training. The STEM issues become very severe when you start to look at our K through 12 education. And let me just give you one metric to set this in light of what reality is. Today, one half of all science teachers in K through 12 have never had a science course. That is what we're depending on our future for. You can understand when you see a metric like that why the work of Chris Hailey and many like her is critical to ensuring that we have a workforce of the future that is second to none. And the work is daunting. It's a lot ahead of us. But thanks to the work of Chris and others, we are very excited about a future that is full of possibilities. And let me tell you a little bit about Chris Hailey. So Chris is a part of the College of Engineering's team, part of Scott's team. She is the senior associate dean in that college, and she's a professor of mechanical and aerospace engineering. And having a son who's an aerospace engineer, I know Chris is an anomaly. She is someone that I think we can be extraordinarily proud of, partly because she not only does she exemplify the quality of engineering and the engineering quality that leads to success in grantsmanship, in great teaching, and of course in effective outreach, but she also is a woman in that field. And we be very proud of what that means in terms of the role model and the possibilities for the future. She's a licensed professional engineer, which means not only can she teach, but she knows what she's doing. She can actually make it happen. And we're very proud of her that way. She came to Utah State University from Sandia National Labs. And for those of you who might know a little bit about Sandia, this is a place where excellence is called for in all employees, and everything they do is part of the national defense system of making sure that our science is ready for any emergency or any concern ahead. She's a recipient of numerous awards, a Teaching Excellence Award from the College of Engineering, Educator of the Year Award from the Utah Engineers Council, and a Society of Women Engineers Distinguished Engineering Educator Award also. She is currently the Director of the National Center for Engineering, Technology, and Education, and you know, just downright, she's a great lady. This is someone I'd be proud to stand behind any place, anytime. Please welcome Christine Hailey to the podium.
Thank you, Vice President Mark McClellan, for the kind introduction. And thank you, everybody, for taking time this morning to come out and learn about some of the important research going on at Utah State University. I appreciate that everybody in this room is probably very, very busy. And to give up an hour and a half of your time, I'm very grateful for your attendance. I'd like to begin the presentation by just introducing an engineering design challenge of interest to high school students. And I'll talk more about this later. You'll see on the right a bath slider system. for a disabled person who needs to take a bath, the person is seated in the chair, often strapped in, and then the chair is slid over the bathtub, and a caregiver will bathe the person, shower them with some sort of shower wand. Well, engineering is approachable in a high school level. If you sort of pose to young people, we need a system that's more portable, less expensive, less complicated. What do you think that would look like? So that gives you an idea of the kind of design challenge that I'm talking about. Why would high school kids care about redesigning a bath slider system? One of the things we've come to find out in our 8 years of research is that high school kids like authentic problems, they like situated problems. What we mean by authentic are real-world problems, problems that are important to them, and what we mean by situated are problems that sit within their social context, their cultural context. In other words, they have to work on problems that they're interested in. And that probably comes as no surprise if you've got a teenager at home. As Mark alluded to, we're interested in introducing engineering design thinking in high schools for a number of reasons. And it really is about this STEM initiative, the importance of science, technology, engineering, and math. There's a big disconnect, and it's a growing disconnect in this country, between the skills we need for a technologically advanced society and the talent that current high school and college students have and we produce. So we're really we're losing ground competitively in the area of technology. Let me continue with that theme. At the national level, you see this play out. The president's advisors have said in order to be competitive, and remember, technologically competitive means important technologies for defense, important technologies for health, important technologies for energy, important technologies for the environment. It's important technologies for the quality of life that we've come to appreciate and expect in this country. We will need 1 million more STEM professionals than we're producing right now. That means we need to graduate about 34% more STEM, science, technology, engineering, math majors than we do right now. If you take it at the local level, some of you are familiar with the governor's initiative, Prosperity 2020. This is a very, very important idea that by 2020, 66% of the young people in the state of Utah will have some sort of post-secondary certificate or degree. It's a noble goal. Last September, so just about a month ago, he also said it's important to introduce the STEM Education Workforce Partnership because his other goal for 2020 is to move the Salt Lake City area into the top 10 cities known for technology. And of course, what that means is lots of jobs for people, lots of excitement. It means we want to become like Silicon Valley or Boston. So these are goals not only nationally, but they're also goals at the state level. For the past 8 years, I've been the director of the National Center for Engineering and Technology Education. It's been funded by the National Science Foundation. And we've been looking at a lot of issues, it comes as no surprise, relative to engineering and technology education. I'm going to talk about just one notion, and that is the idea of engineering design in high school. So basically, I'm going to talk about 3 things. Why would you be interested in having high school students participate in engineering design? What does engineering design look like for high school students? And what kinds of engineering design challenges might motivate all high school students? Throughout this conversation, if I fail to do this, it's very important that you understand that we're interested in engineering design for all students. If you think about these STEM initiatives and the importance of increasing the number of graduates in science, technology, engineering, and mathematics, that means we need to reach populations we haven't reached before. women, underrepresented minorities. That's how we're going to backfill or fill this need. And so our goal in this whole conversation and in all of our studies was we're interested in this experience for all learners. So what is engineering design? Well, engineering design allows students to tackle ill-structured problems. By that, I mean there's no single right answer. In fact, the goals are a little bit ill-defined. The information is less than complete. So the students grapple with a real-world problem. We all grapple with problems where the first thing we have to do is make sense of what is the problem. So there's great value for learners, all learners, to grapple with ill-structured problems that permit many solutions. And what we're interested in, and I'm an engineer, so would be solutions to problems in the human-made environment, technology kinds of solutions, and I think for high school students, solutions that impact the quality of life. Engineers have something called a design process. We're rather structured in our approach to solving technological problems. And we feel there's great value for all learners to structure their thinking when they're grappling with a problem, particularly a technological problem. So we want them to arrive at a solution through a process. And of course, if it's engineering, we have to pin some math, science, and technology onto the solution. So that's what engineering design is. Let me tell you what we think it's not. We don't think engineering design is gadgeteering or tinkering. Students really like to tinker, but we don't think that's engineering design. Students like to immediately go and cut and try, and if it doesn't work, cut and try, and if it doesn't work, cut and try. But throughout that process, not gain any insight into the fundamental physics or the fundamental science that underlies the problem. Engineering design is not a craft activity. I'll give you an example. We were working with some teachers in introducing engineering design in their high school setting, and one teacher came back and she reported that it had been an absolute success. She'd come up with the perfect design, and that was a pinwheel. So she brought in construction paper, she brought in dowel rods, she brought in pins, she brought in directions, she brought in scissors to high school students, and it was amazing. Every high school student could indeed construct a pinwheel. That was lovely, but it's not engineering design. Engineering design also is not scientific inquiry. Scientists also have a very logical way of grappling with complicated, ill-structured problems, and that's a good way for students to learn to think as well. But scientists tend to try to figure out why something is happening. And they're happy once they've figured out why something is happening. So the outcome of scientific inquiry is an explanation of what's going on in the physical world. The outcome of engineering design is a product or some sort of process. So the outcomes are different, which means that the thought process are a little bit different. So what engineering design is, ill-structured problem, we think of value for all students. What it's not is gadgeteering or scientific inquiry. Okay, so what are the goals? Well, at the top we say engineering habits for all. Engineers have a habit of mind, we call. We have a way of thinking that we believe all citizens should be introduced to for a number of reasons. It's a way of problem solving. Engineers tend to be systems thinkers. We understand that most problems consist of a series of smaller, interrelated problems, and all of these little interrelated components must work together for a solution. So it's really, I think, of value for kids to think largely at a system level. It's a way to introduce science, technology, and math in a real-world problem, so it's opportunity for STEM concepts. Our goal is not to turn every high school student into an engineer, but it would be great if more students became interested in engineering. And maybe through a high school level engineering design experience, kind of get some confidence that engineering might be an approachable profession for them, particularly for women and underrepresented citizens. Finally, technological literacy is really important. Even if somebody passionately decides they want to be a poet, well, more power to them. But if they have gone through some sort of engineering design process where they've, for a little while, seen what's the underpinnings, what's the backbone of an engineering kind of solution. Gosh, what went on when people thought about designing automotive airbags? That makes them more informed citizens. And so technological literacy is also very important. This is a picture of an engineering design process that professionals or experts would do. Just as a side note, there's a lot of research on trying to figure out how teams of engineers solve problems, because this solution technique, trying to get into the mind of the engineer, is very important for innovation in this country. And if you can begin to draw maps of how people think about engineering, then maybe you can facilitate more creative thinking in your plant as a working engineer. So this is a very complicated map, but it gives you some idea of engineers often begin with defining objectives, constraints. They concern with evaluation, sustainable strategies. They plan next phases. They test, they verify, and it's very, very iterative. We don't expect high school students to do that. After we've conducted quite a bit of research, and others across the country, we've come up with what we think is a better model for the engineering design process for high school students. It looks like this. We'd like high school students to work their way through these steps in coming up with a technological solution, like the bath slider system I introduced at the beginning. Notice that there are a bunch of arrows suggesting that it may be the case that by the time you get down here and you build your prototype and you test it, it doesn't work. And there's really a lot of value in then going back and starting over. I mean, think about it. How often at home have you worked on a problem and you think you're on the right track and you hit the wall and you have to take 3 steps back? Well, if students would learn, that's okay. That's how engineers think. And it's better to take some steps back. It's better to iterate than to finalize the design and walk away from something that isn't working. So this is kind of this is the anatomy of design. This is what we'd like high school students to be able to do. This is a real challenge for teachers, and I'm very appreciative of that. And I don't know, do we have some high school teachers in the room? I see some very young people that look like they would be high school teachers. This is a challenge for teachers, and I don't want to diminish how important it is that we work with teachers and the power that teachers have in implementing this. But we think that this might be helpful if the problems are relevant and interesting to motivate students, and that's the first thing that's important. It's a little different than traditional work done, say, in a math classroom. Those of you, if you remember back to your algebra class, there was such triumph when you finally came up with the right answer. And you went to the back of the book, and it was there. Do you remember that? It was a single problem with a single right answer. And that's important kind of thinking. But in an engineering design experience, there may not be a single right answer. The teacher may not even know the right answer. So the teacher becomes involved in helping teams of students work on problems. Engineering, by definition, is collaborative. We work together. So now imagine a high school classroom where you've got 5 or 6 teams of students working together. Teachers will need support, and we acknowledge that, for how to facilitate this kind of experience. I'm just going to share with you a glimpse of what high school students can do. I'm going to just walk you through one of the studies we've done. At Utah State University, we run a program called Engineering State. That's between a high school student's junior year and senior year. We bring kids who are interested onto campus, and they spend a week learning about engineering. So it's a really good program, and my guess is, as I look out in this audience, there are some of you who have kindly donated to this program, and I thank you for that. For me, it became a convenient sample of students that we could call upon to investigate, gosh, what kinds of design challenges would you like to work on? What do you see as important problems in your life or your community or in where you'd like to be as you grow up? And so we had some students volunteer, and we had a really bright young woman in the College of Education interview these students. And their students' designs, interestingly, broke into 3 categories. Helping disabled people. That's really important. High school kids have grandparents. They're very aware of the power of technology to assist disabled people. Interesting, a lot of kids were concerned with water. Of course, that comes as no surprise in Utah. They have a very good sense of water. Kids from rural settings have tremendous sense. Water distribution was of interest to kids. And then we actually had a group that were interested in better recreational stuff, like improved climbing equipment. Does that surprise you about high school kids? No, not at all. So I'm going to talk to you just about a group of students. So we selected 4 of them who expressed interest in helping disabled people. They didn't know each other, and we said, would you be willing to get together on some Saturdays and grapple with a problem? And they said yes. And I'm just going to kind of walk you through some of the steps that we saw the students go through as they grappled with this bath slider system. The first thing we really hope students will do is identify the problem. And I have to acknowledge Clay Christensen. Maybe he'll be listening on the recording. He works in the Assistive Technology Lab at Utah State University, and he helped us find this problem. This is a commercial bath slider system. It's fabulous. You slide the client over the tub, and then you move the little sliding part away. It's really expensive. Now imagine this scenario. There's a 19-year-old man. He's got muscular dystrophy. And like many 19-year-old men in this state, he wants to go on a humanitarian mission for his church. He needs to be able to take a bath, but is probably not going to be in the large bathroom at his house. It'll be in some small apartment while he's serving his church. He needed a bath slider system that was more portable, less expensive, fit in more places. And Clay Christensen had come up with a first cut at this. So I want to acknowledge, we presented to students a first cut of this idea and said, look, here are some issues. And we gave them the issues. Could you work on it? And the first step we hoped the students would do would be to identify the problem. So what does more portable mean? Does that mean it fits in the back of a pickup? Is that plenty portable? Or does that mean it's got to fold up and maybe be carried in somebody's backpack or in the back seat of a car? So helping young people move from these vague statements of more portable, less expensive. Well, what's less expensive? $50? $500? $500,000? What's less expensive? Moving students to think about quantifying the constraints is the challenge of identifying the problem. And very closely related then is to begin to do some background research. These are our 4 young students. They didn't know each other till they met on this Saturday. Maybe there's already an inexpensive solution out there and there's no need to go any further. So there they are busily researching the problem. And then what we hope they'll do is develop possible solutions, many possible solutions, because there isn't a unique answer. We're hoping that they've got some constraints, that they've now begun to think about how big is a typical bathtub, how high, how much clearance in a typical restroom if it's an apartment, how expensive can this person, what kind of dollar value can this person afford, what does portable mean, what's easy to pull together, put apart. So we're wanting young people to come up with solutions within what we call this list of constraints, to develop weighting systems for these constraints, because maybe portability to this young man is far more important than cost, so they can work some trade-offs in this multiple problem solution space. Okay? This is obviously the start of where you can plug some science and math in, because maybe you can help the students develop a cost model with math, or maybe you can help the students move to some sort of how heavy was this young man, and what's the relationship between the amount of material you need and this young man's weight. So you can plug math and science in here. And then we want them to select the best possible solution. What we found is that it was really difficult to get these students to buy into a lot of math and science analysis. They did a lot of discussion among themselves, and they had a notion of optimization, but we've got work to do to help them understand that science and math will guide the optimization. Anyway, this is a quote from one of the young men after he'd finished the whole experience, and we're kind of debriefing him about, how'd you come up with the best possible solution? And this is probably more a comment on teaming than anything, that they worked in a group and there were good ideas and bad ideas, and kind of like a diamond. A diamond is kind of unrefined at the beginning, and then the team basically chopped away at the little bits and they got their finished product that they were very proud of. So he had a really innate or an intuitive notion of what optimization meant. Students love this. Construct a prototype. I'm going to go backwards for a minute. We really want students to spend a lot of time thinking about the problem. And some of my colleagues have been timing students while they're grappling with these issues. Expert engineers spend lots of time right here, and they spend lots of time right here. Students, they like to go right here immediately. Let's build it. There's a lot of studies that indicate building is good. It's good for your confidence to see that your idea became something. So this is an important step, but what we really like to do is have students spend more time defining the problem. What we have come to find out is teams of students will spend more time defining the problem than a single student. A single student really wants to drive quickly because nobody's questioning a single student's ideas. You come up with an idea, it's a really good one, let's go build it, compared to this trade-off. And here are the students. They actually, on another Saturday, drove up to Logan and went to the Disability Resource Center and began to construct the prototype. And then they tested it. In the background, I'd like to point out, just so you get some sense, this is Amy Wilson. She's in the College of Education. This is how education research is done. It's kind of new to me because I'm an engineer. So I'm kind of used to breaking things or having things go really fast and quantify how fast. But I've come to find out in education it's very complicated research. It involves people, and you record what the students are doing, and then you go back with teams of graduate students and try to interpret what was it that was really going on there. So I want to point out that I'm giving you an overview. There's lots of hard work that people like Amy have done in the background for this study. Anyway, they tested it. Testing must be against the constraints. It's not against what the teacher wants. They've come up with a list of requirements for their design. Must support a person of this weight. Must fit in a bathtub of these geometries. Must cost less this amount of money. So they're testing against criteria they've come up with, and then we want them to communicate the solution. Many people call this step the opportunity to introduce what we call 21st century workforce skills. Everybody has to communicate in the workplace the products of their work. Either visually, the students in engineering design always give oral presentations. They have to give written presentations. So this is an important step where we pull in colleagues from other areas like technical writing, technical communication. And then finally, redesign. So one of the things the students found out is they'd come up with help from the technician, that's Clay, with a pretty strong slider made out of PVC. Pretty portable, pretty strong, but they hadn't spent enough time thinking about the fabric. If you think of this as a cot, they hadn't spent enough time thinking about the fabric, and it held water. It puddled. And so here your goal is to try to help this person get clean, and this person is sitting in a puddle of soapy bath water. Redesign, and redesign is very, very important. For kids to be able to take a step back and redo in an iterative way promotes a lot of confidence that they can accomplish things. And then this is just a picture of the finalized design with a felt kind of fabric, and you can sort of see it's more portable. The students did not do any structural analysis with this. You must understand that. So again, plugging in more engineering is important. But they could drive to a finalized design. Let me take a step back. In fact, we think it's important in the design cycle to have the students affirm they are done. Now, in engineering, in the real world, product development, engineers are never done. I mean, those of you who own an Apple I, I mean, an iPhone 1, or an iPhone 2, or an iPhone 3, I mean, you know very clearly that professional engineers are never done. They're always refining. The cycle goes on and on. But if this is a unit in a science class or a math class, it's got to finish. And what we found out with these kids is they didn't want to finish. They wanted to come back up on another weekend and redo because they had a lot more ideas. But we said, no, you're done, because it was the end of May. School was almost out. Now, let me take a step back. This was just one example of the kind of research that we've been doing at the National Center for Engineering and Technology Education. We're really a group of 9 institutions. I have to proudly say, though, that Utah State University, we should have had the graphic artists make USU really, really big. Because we're the fiscal agent, we're the lead. We run this center. And the primary goal of this center is capacity building, developing doctoral students who have backgrounds in engineering and technology education to continue conducting research in how students learn these ideas and how to teach these ideas. It's a $10 million center, which you can imagine you'd have to have because we have so many partners. So it's something we're very, very proud of. We probably don't toot our horn enough, but we've been chomping away at some of these problems for about 8 years. I'd like to point out that in this capacity building area, we also were attentive to diversity. There are not very many people in engineering education of color. 33%, a third of our graduates were African Americans, and 25% of our graduates were women. So we're trying to do a number of things in this center, and one of them is to diversify the researchers who look at engineering and technology education. This is a big project. I couldn't possibly have done it. In fact, I've done very little. Mostly I kind of just run HURD on those 9 institutions, if you want to know the truth. There's a lot of other smart people who have really helped move this forward. Kurt Becker's here. Kurt, why don't you stand up for a minute? Kurt's co-PI, and he's in the Department of Engineering Education at Utah State University, and a lot of the research I've talked about belongs to him. Dan Householder, who couldn't come today, is also in the Department of Engineering Education. Jim Dorwood is a colleague. He's an associate dean over in the College of Education and Human Services. And Amy Alexandra Wilson is a young new faculty member over in the M. Eccles Jones College of Education and Human Services. And we could put up 50 other faces because this has been a very, very big effort. I want to also talk a little bit, because STEM is so important to this country, increasing the STEM capabilities of the workforce. We've got other things going on. I didn't put NCET at the top because it's like it's the crown jewel. Put it up there so I could just sort of say, in addition to that, if you look at the blue, these are initiatives going on in the College of Engineering. These are things we work on. SEER, Kurt runs SEER. It's the Center for Engineering Education Research. Scott Hinton, our dean, when he became dean 10 years ago, said, boy, nobody's really studying teaching and learning of engineering students at either the high school level or the university level, particularly the university level. There's just not been an investment of resources on what does it take for kids to learn engineering, and if we knew that, we'd retain more kids. Okay? So SEER is focused on engineering education research, and of great importance to us at Utah State University. As you know, we've got these regional campuses. We've got a 2-year engineering degree in Brigham City. We've got a 2-year engineering degree in Vernal. We've got a 2-year engineering degree in Tooele. Those students take the first 2 years of engineering through distance education. You thought engineering was hard face-to-face. What about now offering calculus through distance education, or offering the first electrical engineering for non-majors through distance education? So one of the primary focuses of SEER is to understand teaching and learning in a distance environment. We have other NSF studies. I'm the PI looking at MESA students, math, engineering, science achievement students, MESA students. We've got MESA programs in Utah. MESA's goal is to reach underrepresented kids. It's an after-school program. It's high school. What's going on in MESA that, particularly in California, has interested more kids in engineering? So we're looking at that. We're also looking at what kinds of design challenges excite high school students who are English language learners. That was just recently funded. I just am waiting. I think it's going to be funded. We're looking at what about calculus delivered in distance settings? What could we do as engineers to improve that? And that's been recommended, but it hasn't been funded yet. I also want to point out outreach. Nina's here. You ought to stand up, Nina, or raise your hand. Research is really good, but there's nothing like having a 22-year-old female engineering student go talk to a bunch of 8th graders about, you could become an engineer. And when you see somebody that looks like you begin to think, oh, dang, if that person could do it, I could do it too. And so we've got a huge outreach effort in the College of Engineering. Nina heads up the Society of Women Engineers. I'm proud to say we're probably one of the most active Society of Women Engineers in the region. That includes New Mexico, Arizona, California. We do a lot of outreach along with other stuff. We have a SHIP program, Society of Hispanic Professional Engineers. They've been able to attract NASA to our campus once a year. NASA comes in the spring, brings all of their cool gadgets and gizmos, and they do outreach to high school, middle school kids. We also have NSBE, the National Society of Black Engineers. Those kids are very involved in outreach as well. If we're thinking about recruiting or interesting other people in engineering who haven't traditionally come to the door, women and underrepresented minorities, it's really helpful to have somebody look like you say, I could do it. And that's what the outreach is about. I'll just mention briefly, Gear Up is a new program that's just been funded. And the goal of Gear Up, Jim Dorwood, who's one of the co-PIs of the NCETE, is to reach low-income kids and prepare them for success in post-secondary education. This is just getting started, but the theme is science, technology, arithmetic, reading, just right in STEM. And finally, if any of you are interested in becoming a director, we're actively seeking a director of the STEM Center, which would help coordinate all these efforts across campus. We put that little E squared up because we think it should be science, technology, engineering, education, and math. We can't walk away from the wisdom that the educators have when we think about how to attract more people in K-12 to STEM, more people to college in STEM. So we're looking for a director, and so apply if you have enthusiasm about that. So, let me conclude. First of all, I have to thank Mark again and Mark's staff. There are a number of people you don't even see who helped put all this together, who helped put these beautiful PowerPoints together for me. So I thank you, Mark, and thank your staff for all of this. I think here's what we've learned. The first 3 bullets. You've got to have authentic design challenges. You may think it's really cool for kids to design trebuchets, but not all kids think trebuchets are cool compared to maybe some sort, I know, you and I, we are kindred souls, but truly, some kids are not interested in things like trebuchets or marble sorters. They're much more interested in designs that make a difference in their community. And so you could see working with people with disability because often they have grandparents who have physical limitations. Clearly, students like to build more than they like to define the problem or analyze, and this is something we have to work on because we really want them to spend more time defining the problem. But I think there's a growing body of research over the past 5 years, both within the center but across the nation, that when students engage in engineering design, all students, We see gains in science and math understanding, and we see tremendous gains in interest and confidence for these kinds of experiences. Problems to still work on. If we want all students to have an engineering design experience, where would you put it? Does it go in the math class? Does it go in the science class? Does it go in the technology class? Does it take a team? It's not clear yet across the country where this opportunity might fit. And there's got to be continued research on what are appropriate pedagogical strategies for all students. I'd like to conclude by saying that certainly STEM and developing a STEM workforce is a national imperative. I've been, you can see by my gray hair, at the university for a while. I tried to count the other day how many students I've taught. I stopped at over 1,000. But I can tell you this. My experience with these Utah students, a lot of them now, in a really exciting course called thermodynamics, something you're living for, I'm sure. The Utah students who make it to thermodynamics are bright, they're innovators, they're very capable, and so I feel like the future is really bright whenever I look at these really capable engineering students that we have. We just have to have strategies for more. Thank you.
Programs we're talking about at the current level of funding?
It's a really good question. Do we have anybody who wants to answer that before I do, who's more informed? No, I mean really, because I have an answer, but I don't have a particularly informed answer. Yes? Would you like the mic?
Sure.
Are you running for office?
What's that?
Are you running for office?
I am.
Oh, okay. I'm Chris Hailey. Okay.
You know, it's true. I'm Senator Todd Weiler from District 23 in Bountiful. Utah does rank 51st, actually, in the per pupil funding. I've only been in the legislature for 9 months, so you can't blame me for that. I will tell you this. We added $115 million of new money to public education this year under my watch. But to be fair, we have a unique culture in Utah. We have large families. We have a lot of one-income households. And we have a state where we only control 1/3 of our lands, so we can't get the revenue off of the other 2/3 that are owned by the federal government. So we're trying to find Utah solutions to those Utah problems. I want you to know, out of the discretionary state funds that we have, which is $5.4 billion this year, we spend exactly 49% of that on public education and 15%, additional 15% on higher education. So 64%, nearly 2/3 of our entire state budget, of our state funds, we spend on education. Now that's not good enough, but if you rank what percentage of our entire state funds that we're putting towards education, we're near the top of the 50 states. And so I just want to put that in perspective. We're trying, but we face some unique challenges and we're working on that. Thanks.
You gave a good answer, better than I could have. Thank you. You can sort of see that at some level, I really am an academic. My own sense of it in answering you is that the solutions that are working today will not be as effective in 10 or 15 years if we just look at the shifting demographics in the state. And so as we look at emerging populations that maybe have never been to college, maybe in the household haven't even graduated from high school, a lot of the notions that education can partially be handled at home, I think, will shift. But my sense in Utah, is that this is a state that values education as much as any state. And if we sort of see, if you look at standardized testing and other sorts of things, we're running with the pack. And so my own opinion is when we see those scores slip, which we might, when we see those scores slip, I think we'll do something. But I'm an incredible optimist. I believe both sides will work on this across the aisle. That's my perspective. Yes.
Dr. Hailey, talking about, some of the underrepresented segments. For instance, young women. Do you have any research or anything that would tell you when, within the life of a young woman or a girl, as it were, we are losing them culturally to the concept of, wow, math and science and technology, that's cool,
Yeah.
rather than this isn't something that my segment does.
Yeah, I think that's a very good question. First of all, it's not just a Utah problem. Across the nation, if I just talk about engineering, only about 20% of the engineering workforce, only 20% of the graduates are women. But there's nothing particularly male about engineering. I mean, if you think about the bathtub slider problem, that's a problem for all people. So it's a national problem. Utah is not quite as good as 20%. We're closer to 10% of women completing STEM degrees, engineering degrees. I think it begins in elementary school. I'm going to tout a program called Engineering is Elementary, developed by the Boston, help me, Kurt, Science. Boston Museum of Science, thank you. Boston Museum of Science, which introduces engineering with readers. So we're combining two kinds of thinking with some sort of geography lessons about, somebody in I don't know, let's say Brazil needs to build a bridge, and so you learn a little bit about Brazil and you learn a little bit about what's going on in the rural setting, and now you're a first grader and you have 2 chairs and some materials. How might you think about a bridge? And every kid relates to that. So you've got to start, I think, really early on. I think studies have shown by middle school we lose women to these areas. We probably need more relevant kinds of designs. And you'll begin to see this. There are now, I don't want to say pink robots because that's too stereotypical, but there's great interest in having designs that are of interest to women, so that they get hooked in. Science. So, but it's a challenge, but I think it's been studied and we're working on it. All of these problems are systemic, and you would probably say this as well. So the notion of the importance of systems thinking for people, there's a lot of interrelated parts, and you can't just sort of say, well, we will now make all 8th grade women do something special. It's much more complicated than that. So I don't have a real good answer for you, other than it's got to start really early. What we see at USU, by the time women declare interest in engineering, we keep most of them. I teach a women in engineering seminar. Nina hooks them into SWE. We're pretty good about retaining them if we get them. Does that help you?
It does. I'm someone who feels we can't afford to throw away half our talent.
Yeah.
Or let it drift away.
Yeah.
Do you think that anything like the interest in electronic gaming that a lot of people are into in the electronic toys is becoming more accessible, for instance, to women?
Oh, wait, think about, now I'm going to really show my age, but in Facebook there's like that farming activity. Somebody help me. See you in the tie. What is that farming activity? Farmville. Farmville and the whole way of thinking about buying and trading and all of that sort of stuff is very appealing to women. If we thought a little bit about taking Farmville to the next level, which maybe would be infusing a little bit of science about stuff growing, I think it'd be very accessible. I'm also hopeful that because this is a national problem, that PBS and other places have these design squads now. And the design squads aren't just a bunch of Dilbert kind of people. Do you know what I mean? They're also women, they're people of various ethnicities. So I think it's a national movement, and we need young people to see that engineering and science and math is pretty cool. That it's not just for nerds. Sometimes we're our own worst enemies because we like to think we're nerds, and we sort of hold that high as something we're proud of, rather than talking about in middle school, gosh, there are a lot of problems that need to be solved. Think about when you have a premature baby who's 2 pounds. Who keeps that baby alive? Oh, doctors. Wrong, it's engineers. It's all of the gadgets that the young little 2-pounder is hooked up to. That's the sort of hook, and it's our fault as engineers that we don't promote more the cool stuff we really do. Does that help? Yeah. But I don't have an answer. I haven't solved it yet. Sir?
It's kind of a two-point question because 3 of the kids that grew up next door to me are all engineers. They're all in their 40s and 50s now, and they all have to go out of state for their jobs. So if more Utah high school kids got interested in STEM fields to go into, first, could the Utah universities absorb them? And second, if Utah universities could produce more graduates in STEM fields, would that help economic development, bringing in non-high-tech jobs here so that they could stay here instead of leaving?
Well, I think the answer is positive for both of those. I'd like to answer your second question first, which is why I think the Prosperity 2020 and this notion that one of the goals is to have a technology center second or, in the top 10 will bring jobs to Utah. I mean, I think Gary Herbert works on that. But I think he needs more engineers, more high-quality research kinds of institutions as well, because that draws outside companies. So I do think, I'm not saying this well, it's a chicken and egg kind of problem. If you produce them and you've got good research, industry will come. If industry's here, they're going to demand more high-quality engineers and more high-quality research. So I think Herbert's got an idea. Let's make that a goal. So that's the first question. I'm tempted to put my boss on the spot. So Scott, what do you think? Do we have capacity for more engineering students?
Yeah, there are.
I'm going to hear about this later.
Many of the disciplines within engineering are below capacity at Utah University. For instance, at Utah State, we can probably double the number of biological engineering students without having to do much. That's a young program that's going to start. On the other hand, mechanical engineering is huge. And there's not enough capacity in the state of Utah for more mechanical engineers. They're BYU, University of Utah, Utah State, they're all very full. Electrical could grow, civil could grow, environmental engineering could grow. So most of them, we really, there's not huge capacity, but, over the next few years, 10, 15%, we can handle that growth. And then hopefully as the economy grows, there's more money, and then we can get the legislators to find more engineering initiative money. So that's the chicken and egg problem too. But there is capacity that things starting to pick up slowly, which we will.
Okay, one last question.
Chris, just one point on the question this gentleman raised. I served on the Engineering and Technology Initiative Advisory Board since it was formed by and the last survey we did, the best count was there were about 7,000 needed engineering positions for engineers vacant in the state of Utah right now. 7,000.
Maybe just one final thing is I'm not being fair to my science, technology, or math brethren and sistren. The initiative really is to underpin, I love engineers, can't help it. But it really is this more, we need scientists, we need mathematicians, we need technologists. And so it's really an integrated approach.
Great job, Chris. I love the analogy of the chicken and egg. If you look in Cache Valley, we have Campbell Scientific, they're expanding, using engineers. You don't attract someone like Adobe here to this state without a workforce that is technically trained. I think the answer is absolutely, we have the capacity for more. And as in the chicken and egg scenario, as you build that capacity, I really do believe they will come. If you enjoyed today's presentation, and we touched on the issue of people and the intensity and need for a technical workforce, you also start to expand and see so much of the issues we struggle, whether it's management of water, management of workforce, is a people-related issue, and it ties to our society. So our next presentation at Sunrise in February 1st will be focused on people by one of our best sociologists, Doug Jackson Smith, and he'll be looking at the management of water resources from a society perspective, from a people's perspective. I guarantee you will enjoy it as much as you've enjoyed Christine. Let's give one more hand to our best engineer, Chris Hailey. Thank you all for being here.